Hello, welcome to our Project 1 for Physics 213 by Maya Golia, Ali Karsaboom, and Aaron Hume. The first section of this project is the Understand and Plan section. From the three options for this project, our group decided to analyze the strip. The information that we gathered from the problem statement was that we have a thin strip of charge or wire that's located in the XY plane. So this thin strip of charge, aka wire, is said to be very long in the X direction and have a width of 2L in the Y direction, which is important for our assumption section later on. The function sigma of y is equal to sigma naught y over L gives us a charge density. And so our job is to determine what the electric field and electric potential are at every point along the y-axis, with y being greater than L. Our four assumptions for this project are 1, the electric potential is equal to 0 when y is equal to 2L. And so this is important for setting up the bounds of our integrals later on in the calculation section. Our second assumption is that the wire is infinite in the x direction because in the problem statement it says it's very long in the x direction, so we assume that it's infinite in the x direction. And our third assumption is that the center of the wire is at the origin. This assumption is vital for the rest of our project because centering the wire at the origin allows for symmetry in the x and y directions, which is extremely useful in setting up our integrals. The last assumption that we have is the variable a is any point on the y-axis, and the variable y is any point along the width of the wire. Having these two variables defined and having them separate for these two different distances is useful in setting up the integrals in our calculation section again. For our charge diagram, which is located on the left side of the screen, we evaluated the function of the charge density sigma naught y over L with respect to a changing y value. As y gets closer to 0, the numerator of the function gets smaller, which causes the charge to decrease as well. Therefore, as you move away from the x-axis, which is where y equals 0, the charge increases in magnitude. On the right is a diagram with labeled vectors. The chop of charge dq has an r distance that extends from the location of dq to any point along the y-axis. The distance from the point on the y-axis to the wire is defined as a, while the height of dq with respect to the width of the wire is defined as y. Since we are utilizing the infinite wire assumption in the x direction, we know that the electric field will be extending upwards in the y-hat direction because we are only looking at the points on the y-axis that are greater than L. Therefore, we need to compartmentalize the dE vector into x and y components and find the y component specifically. To find the y component of the dE vector, we utilize trigonometry to show that cosine theta would give us the electric field only in the y-hat direction.
In this part of our video, we'll be talking about how we did our calculations to solve for the electric field and the electric potential. These are some of the equations we used. The first one we used was our electric field equation, which is 2k lambda s squared over s hat. And then our second one is our sigma times the area, which we inferred would be dx dy is equal to r dq. And then our delta v, which is our change in electric potential, is equal to the negative integral from Ri to Rf of the electric field dr. And then in the equation we are given our sigma in terms of y, which is equal to sigma naught y over L. And then our last equation we have here is our electric field for our object, which is k dq over r squared r hat. For the first part of this project, we were asked to calculate the electric field. To start, I used our electric field formula, which is equal to k dq over s in the r hat direction, where k is going to be a constant. Then I knew that dq was equal to sigma of y dA from one of the formulas in the equation slide. Then I plugged that in, so I got 2k sigma of y dA over s, and then it would be in the r hat direction. And then I knew dA would be in the dx dy direction because that is where our strip is located. So then I would get 2k sigma y dx dy over s. Then the next step was to find what our s or r is equal to. So I knew that it would be equal to a minus y squared plus x squared. Then I would plug this into where the s is located. So then I would get E is equal to 2k sigma y a minus y squared plus x squared dx dy in the y hat direction, because that is the direction of our field. Then I would plug this into our integral, and it's going to be a double integral because we have dx and dy. So our bounds for our integral will be negative infinity to infinity for the dx, because our y is infinite, which we defined in our assumptions. Then for our dy, we use negative L to L because that is the length, the height, the width of our strip. So then I plugged everything into our formula, including our sigma y, which was sigma naught y over L. So I plugged that all in, and I got the integral from negative L to L, and then negative infinity to infinity of 2k sigma y over L over a minus y squared plus x squared dx dy y hat. And then I knew, because we're looking at our r vector, that it needed a cosine of theta, so then I plugged that into our integral as well. And so this came out being the integral from negative L to L of negative infinity to infinity 2k sigma naught y over L over a minus y squared plus x squared cosine of theta dx dy y hat. So then after solving this integral, I got E equals 2k sigma times lambda of a minus L minus the ln of a plus L plus 2a over a minus L, and then a plus L. The second part of our project was calculating the electric potential with the electric field that we just calculated on the previous slide. So I used the equation from the equation slide, which is the change in electric potential is equal to the negative integral from Ri to Rf of the electric field dr. So then I restated our electric field equation and then plugged that into our integral, which I got the change in electric potential is equal to negative from integral from negative L to L 2k sigma times ln of a minus L minus ln of a plus L plus 2a over a minus L plus times a plus L in the y hat dr. And our bounds are from negative L to L because that is the width of our strip. Then I knew the change in electric potential was the final electric potential minus the initial potential, and then I plugged that into our formula. And next, I knew that the final electric potential would be 0 because that's when y is 2L. So then I used that assumption for the next part. So then I got negative v initial is equal to the integral of negative L to L 2k sigma times ln of a minus L minus ln of a plus L plus 2a a minus L a plus L y hat dr. Then I knew that dr was equal to y hat dy, and that when y hats multiply together, it would equal 1, so then we're just left with dy. So then I got the integral of v, the electric potential initial, is equal to the integral from negative L to L of 2k sigma ln of a minus L minus ln of a plus L plus 2a over a minus L times a plus L dy. Then after solving this integral, I got that the electric potential is 2L times 2k sigma ln of a minus L minus ln of a plus L plus 2a over a minus L times a plus L. The next part of this problem is to sense make to make sure our answer makes sense.
Sense making, physical answer. Here we have the two expressions that we ended up with, and right now they're a little bit hard to make sense of. So to help with this, we are going to look at our other sense making strategies so we can better support our answer of why these do make sense.
For our group, the first part is doing our units to make sure that they cancel out to get the units that we want. So we start with our electric field equation. So 2k sigma times ln of a minus L minus ln of a plus L plus 2a a minus L a plus L in the y hat direction. And I know their length is going to be in meters, k is going to be Newton meters squared over Coulomb squared, sigma naught is coulombs over meters squared, and we're trying to get newtons per coulomb. So after plugging this in, we end up getting newtons per coulomb, which is what we wanted. And then for electric potential, we did the same thing. We used our electric potential equation, and then we plugged in and we knew what the values were, and we ended up getting newtons per coulomb, which is the value that we wanted.
Sense-making special case analysis. When we set the initial sigma to 0, the charge for the wire would also be 0, which means the electric field would be 0. Since sigma is in the numerator, if it goes to 0, then electric field would also go to 0. And since the change in electric potential relies on electric field, if electric field is 0, the change in electric potential would also be 0. And since the electric potential final is 0, that means electric potential initial would be 0. This would make sense because if sigma naught was 0, that means the charge density would also be 0 to begin with, which means there's no charge, and that would make the electric field and electric potential 0, which does make sense. Sense-making covariational reasoning. For the electric field, if we increase A for A is greater than L and less than 2L, it will decrease the electric field. This makes sense because the further away you are from the electric charge, the less the electric field is. Since electric potential relies on the electric field, just in the way that we solved it, changing any variable in the electric field will also change the electric potential in the same way. So if you increase electric field, the electric potential is also increased. This makes sense because of the relationship between them. Since the electric potential at 2L is 0, any point beyond those values in the y-hat direction will have an electric potential of 0 as well. Same with negative 2L. Anything below negative 2L will also have an electric potential of 0. So we set the final electric potential to 0, meaning that we can solve for the initial electric potential at any point between L and 2L, which is why the electric potential is directly affected by electric field. It's because they are proportional as seen in this equation. For our reflection and similar problems, we chose a studio activity 3-2A, a non-uniform wire. With the problem statement given here, we can see some similarities, like using an integral to solve for electric field and finding the electric field on a point along the y-axis, and also when you're given a non-uniform wire. Some differences, however, are the length is 2L along the x-axis versus this problem we put 2L along the y-axis, and it's the width. And then this problem we also have to solve for electric potential as well, versus the studio problem we only have to solve for electric field. And then we are given the linear mass density in this problem, and it's different from the other one, and it's also in terms of x, versus one we are doing is in terms of y. And this one is solved using a singular integral, and our problem we use a double integral to solve. For our second similar problem, we chose an exercise from lecture, and this is infinite plates for solving for electric field due to an infinite plate. Some similarities is that they're both infinite objects. So this one is a plate, but ours is a strip, which is one of the differences, but they are both infinite. And then we are solving for electric potential using electric field, so we're using the same equation, delta V equals the integral of electric field times dr. Some differences are the directions. So this electric field was given in the z-hat direction versus ours is in the y-hat direction. And then we're given the electric field to start for this exercise versus ours, we obviously had to solve for electric field. And then this one is solving for the electric potential between two constant points, A and B, versus ours is a point, any point along the y-axis that we named A, and so that will change. And that is our physics project. Thank you so much for watching.